solve an example related to the
maximum torque ability.
maximum torque ability or the wide speed control, which means that we can control the speed below the rated speed and above the base speed, what we call, according to the maximum current allowed in the machine. So today I will discuss with you the mode of operation for the machine. Now, you know that the machine can be operated as a motor or as a generator, but in the drive we would call it what? Regenerative braking. And also we have another two modes, but at first let's discuss the mode of operation. So in general, if I need to discuss the mode of operation for any machine, I will draw the torque speed characteristic. So let's assume that this is the torque axis and this is the speed axis. And as you know, in engineer, the plus and the minus is sense of direction. So I will assume that this is the positive direction of the torque and this is the positive direction of the speed. So you know that any rotation system can rotate either clockwise or counterclockwise. So there is no meaning for plus and minus. As engineer, we use the plus and the minus as sense of what? Of direction. And if I need to discuss the mode of operation, I must fix the field direction. Otherwise, I cannot say the motor is rotating clockwise or counterclockwise, because if I rotate, let's say, exchange the direction of the flux, it will rotate in the other direction. So if I need to discuss the mode of operation, I need to fix what? The direction of the field. So here I will discuss with you the mode of operation. Huh? The mode of operation. Now let's see. In general, let's assume that we have plus minus here, which is the VA. And let's assume that here we have the plus and the minus here, which is the EA. Now, in general, for the motor action, VA must be greater than EA. Of course, here we have a resistance in between, which is the RA. But simply, I will assume it's inside the machine. Huh? So for the motor, in order for the machine to draw a current, in this case, VA must be greater than EA. Yeah? So here in the first case, I have that VA is greater than EA, and both are positive. Yes? Now simply, if VA greater than EA, then the current will flow from the supply to where? To the machine. So this is the IA. So IA is positive, correct? If IA is positive, TE is positive or negative? Remember, I'm fixing what? The flux. So now the direction of the torque depends on the direction of what? Of the current, correct? So the torque is what? Is positive. So simply, this means that the torque is positive. And because the back EMF is positive, and I'm fixing the flux, then this means that what? Omega is what? Is positive, correct? Yeah? So the power is positive or negative?
Positive.
Is positive. So simply, this is what we call forward motoring. And this is what we call Q1 mode of operation. So in the Q1 mode of operation, the torque is positive and the speed is what? Is positive. Good. Now the same thing. Let's come here. The same configuration. Still I'm having a plus supply and the machine is still rotating in the positive direction, let's say. So here I'm having plus minus VA plus minus EA, except that now EA is greater than VA. So what will happen now?
Regenerative braking.
It's regenerative braking, which means that the current will flow from the machine to where? To the supply. Yeah? So simply the current flow from the machine to the supply, so this is the direction of the current. So simply here IA is negative sign, which means that the torque is what? Is negative. Minus V. Now still EA is what? Is positive, which indicates that omega is positive. So the power is what now? The power is negative. So this is what we call it what? Forward regenerative braking. Yeah? Which means that the machine is acting as what? As a generator, and the power will flow from the machine to where? To the supply. And this is what we call Q2 mode of operation. Q2 mode of operation. Now, let's see here. Let's assume now that the supply voltage is reversed. So this is the VA. And also, the back EMF is reversed, which means that the machine now is rotating in the opposite direction, correct? In the opposite direction. And here I will assume that VA as absolute value is greater than EA. Why here I'm using the absolute value? Because I need to respect the sign. I cannot say minus 20 is greater than minus, or minus 30 is greater than minus 20. Yeah? As absolute value, yes. So VA is greater than EA as absolute value. So simply, this will be the direction of the current, yes? Yeah?
Yes.
So now, the current is positive or negative?
Positive.
Negative.
Negative.
Now, you know that in general, there is two ports for a network. In to the port and out from the port. You should close the cycle, correct? Yeah? So here, the assumption that any current injected to this terminal is the positive sense. Yeah? Now see, here the current is out from the inlet. So the current is what?
Negative.
Is negative. So IA is negative sign, and because EA is negative sign, this means that also omega is what? Is negative sign. So the power is what? Negative by negative is what?
It's
Positive. So it is positive sign. So this is what? The machine is acting as a motor or as a generator, let's say.
Motor.
As a motor in the
Reverse.
reverse direction. So this is the reverse motoring. And this is actually Q3 mode of operation. Yep. Now let's see in the last quadrant here, the same configuration, except that the back EMF as absolute value is greater than the absolute value of the input voltage. And here I will assume that the back EMF as absolute value greater than the VA. So now the current will flow from the high potential to the low potential. So now the current is positive or negative?
Positive.
Now in this sense, the current in, so this is the in port. So IA is positive sign, which means that the torque is positive sign. And EA still negative here, which indicates that omega is negative. And the power
Negative.
will be a negative. So this is what?
Backward.
Reverse generator.
Yeah, this is the reverse regenerative
Braking.
braking. Good? Yes? Okay. Now, we have another mode of operation we call dynamic braking. We call it what? Dynamic braking. The meaning of the dynamic braking is what? I will disconnect the supply, and instead of the supply, I will connect what? A resistor. What's the idea behind the dynamic braking? I need to stop the machine. Yeah? But you know that if I'm turning off the supply, the machine will do what? Free run. Because the machine has what? Kinetic energy. Yeah? And it will stop where? It will stop when the kinetic energy will vanish. So now we will use external resistance in order to dissipate the energy. Of course, later on we'll say that no, I will recover the energy to the system. So now we have another mode of operation, and this one we call the dynamic braking. The dynamic braking. So here. Now it's similar to the regenerative braking, except that let's assume this is the field, fixed field. I'm not changing the field. This one is fixed. And I'm assuming that the machine was rotating, which means that here I'm having plus minus EA. Now, in the regenerative braking, what will happen? Instead of the supply, I will disconnect the supply. So here I will assume that I'm having a switch, and here I'm having a braking resistance. And let's assume this is one RB, this one is RA. And now the switch is going from, let's say, position 1 to position 2. So I'm disconnecting the supply, and I'm connecting what? A braking resistance. So RB is what? Is the braking resistance. So who can calculate IB here equal to what?
EA
EA
على
over B.
RL.
So simply, I brake is equal to what? EA over R total, which is RA, plus RB. And EA is equal to what? It will be K phi multiplied by omega over RA plus RB. So if I need to plot the characteristic for this machine, let's assume that this is the torque and this is the speed, and let's assume that this was my torque speed characteristic, and let's assume we have a unidirectional load, gravitational load. So this is the point of operation, Let's assume that this TL here. And the machine was rotating at this speed. Let's assume this speed is omega 1. Yep. Now, we did a dynamic braking. What will happen? Yeah, the speed should be reduced. But how? The first thing, the torque speed, the new torque speed characteristic will cross the torque or the, let's say, the x-axis at which point?
Torque equals 0.
At 0. Yeah, at 0 point here. Why? Because this point is for 0 volt. Yeah. So simply, let's assume that I'm having the following torque speed characteristic. Huh? It's supposed to be parallel to that one. Yeah? Of course, it's supposed to be parallel to that. Should I try to change it? No? No. So you are getting the point, huh? Okay. So now what will happen? In the first stage, this torque speed characteristic now is forbidden. The machine will go to the new torque speed characteristic, enter into to the Q2, which is the regenerative braking. Then it will start to deaccelerate, yeah? Deaccelerate until crossing the 0. Now, at this point, if I engage a drum, mechanical drum, the machine will stop, yes or no? At this point at the torque equals 0 and omega equals 0, correct? So imagine that I'm disconnecting the load. Imagine that I'm disconnecting the load. And I'm engaging a drum. What will happen? Huh? It will stop actually. Actually, at this point, if I'm disconnecting the load, it will stop. At this point, if I'm disconnecting the load without the need of a mechanical drum, mechanical brake, it will stop. Why? Because at this point, the torque equals 0. And omega equals 0, so there's no power. Stand still. Yes? So simply at this point, I can stop the machine if I'm disconnecting the load, for example, at this point, T equals to 0, and omega is equal to 0. So if the load torque is disconnected, then the machine will stop. Yes or no?
قبل ما نشيل اللود مش مفروض توقف الماشين ولا لا؟
بس هي بتعمل دي accelerate.
Just a minute. If the load is connected, what will happen? Only I'm doing dynamic braking, which means that I'm disconnecting the voltage, and only I'm adding a braking resistance, and I think you all understand why I'm adding that to limit the braking current. Yep. Now, if the load is there, what will happen? Where the operating point will be? This one. So the machine will never stop. Yes. Yes. You know that the operating point is the intersection between what and what? Between the torque speed characteristic of the machine and the load. Yes? Now, the first line was the torque speed characteristic of the machine at certain voltage. Let's say VA. Rated, let's say. So, this one was my operating point. Now I'm disconnecting the supply. So VA equal to 0. So now this is my new torque speed characteristic that the machine should obey, let's say. Yeah? Now the operating point is decided by what? The intersection between the torque speed characteristic of the load and the machine. So at this point, if there is no load, yeah, if I'm disconnecting the load, the machine will stop here. Yes? Yeah? Why? Because TL is equal to 0. And simply this is the intersection point between the 0 torque of the load and the 0 torque of the machine. Now, if the load is there, the intersection point is here. So the machine will do what? Huh? Regenerative braking, yeah? So it will accelerate, correct? Until reaching to this point. Yeah? This is what? Under the effect of the load, huh? Correct? Understood? Yes? Good. So now, let's see. If I replot here the same characteristic, except that I will change the RB. So let's assume that this is the first one, this is the second one, and let's assume here I'm having another one somewhere here. Yeah? That can be like this. So now from here I will do a dynamic braking and I will follow one of those lines. Yeah? According to what? To R total 1, let's say, R total 2, R total 3, where R total is what? Is R total of I is equal RA plus R a braking of I. So simply here I'm assuming that I'm having 3 different values of the braking current. Huh? Good? Now the first question. Which line for the smallest braking current, braking resistance? So simply here I'm having 3 lines. Yeah? So the first line, let's say 1, huh? 1, 2, and 3. For which line the resistance is the smallest?
3.
3.
Slope.
Yeah? Good. The slope is what? Is this. So simply this means that here, this means that RT3 is less than RT2 less than RT1. For which line the machine will stop faster?
R1.
1.
R1. 1. Who say 1? Raise the hand. The other. You have other? Huh? The other. For which line from 1 to 3 the machine will stop faster? Which means that the machine will stop faster if follow the, let's say, RT1 or under RT2 or under RT3. Now, in the class, all of your friends say what? The first one. Yeah? What about you? What about you? You have answer? Why? Huh? RT1. So you agree with them, huh? Yeah. You know that is the better, huh? To die with all. Huh? Yeah. No. Actually, it's the third one. Huh? Oh yeah. I know. Now, all of you is genius actually, and you are thinking like Basit. Simply measure the distance here. Huh? This one is the shortest distance. So simply the shortest distance is what? Is the fastest. Huh? But you are missing something. This plot is not omega with respect to time. This plot is what? Torque. So the highest braking torque, the fastest the machine will stop. So simply for the third line, I'm generating the highest braking torque. So I will stop faster. The first line, I will generate the minimum braking torque. So logically I will stop what? Slower. Yeah? So this plot is not between the speed and the time. It's torque speed characteristic. You have no indication about what? About the time measuring the displacement. Huh? So here simply the minimum braking resistance, the faster that the machine will stop. Why? Because I'm generating higher braking torque. Higher braking torque. Good. So simply, this means that.
دكتور.
Yep.
كل ما كانت البريكنج ريزيستنس أقل كل ما كانت البريكنج تورك أعلى.
Yeah. So simply, someone will say put RB equal to 0. Yes. And this is what will stop the machine like this. Yeah. But simply, maybe you will damage the machine due to the overcurrent. Yeah. That's why we add here what RB to limit the braking current. So RB is what? Is put it there to limit what? The braking current. Why? Because I need a mechanism to dissipate the energy. So the energy either can be dissipated inside the machine, and it's dangerous. Yeah? So what I will do, I will dissipate it outside. Yeah? So now here I can open a lot of problem to design RB. Either based on time, I need you to design RB such that the machine will stop at t equal, let's say 2 seconds, for example. Or I will tell you that design RB, the braking resistance, such that the maximum current is not allowed to exceed 4 times the rated, for example. No? So you have a lot of, let's say, scenario to do that. Good? Understood the meaning of the dynamic braking? Good. Now, also, I'm having something we call plugging. Do you know the plugging? The last mode of operation, we call it plugging. Do you know the meaning of the plugging? Huh? Simply imagine that the machine was rotating in certain direction. Let's assume it's opposite direction. So let's plot here schematic or circuit for a simple separately excited DC machine, and let's assume that I'm engaging the following plus minus VA, let's assume, and this LA RA plus minus VA, and all the time here I'm discussing the field is what is fixed. Huh? I'm not changing any parameters, let's say, in the field circuit. Now the machine is rotating. And let's assume it's rotate clockwise, and the clockwise is the positive. Huh? You know that there's no meaning for clockwise or counterclockwise, positive or negative. Let's assume it's positive. Huh? Okay, it's positive. So a current will flow here. Huh? A current will flow I, A, and we know that at steady state, IA is nothing more than what? VA minus EA over RA. Yes? Yep. Now, imagine someone of you say that I will reverse the direction of the supply. Yeah? The supply was plus minus, now I will exchange it to be what?
Minus plus.
Minus plus. So, in the plugging, I will plot only the armature circuit here. Now, what will happen here?
ما في سبلاي.
Eh?
ما في سبلاي.
كيف ما في سبلاي؟ غير سبلاي.
Now here, those two supplies resist each other in the first scenario. Those two supplies, let's assume that VA and EA are two supplies. Are they resisting each other or supporting each other? Resisting. Here,
Support.
they are supporting each other. Yes? Yes? They are supporting each other. So similarly, listen what? Now, the current will flow in the opposite direction, correct? Yeah? Okay.
Very high.
Very high current. Very, very, very high current. Huh? So if I need to plot the torque speed characteristic, what will happen? And I'm assuming here VA, here minus VA, correct? Yes? So simply, if this is the torque, and this is the speed. If this one was the torque speed characteristic for the first one, this will be the torque speed characteristic for the second one, correct? Let us see. Let's change this one slightly. So let's assume that this is the torque speed characteristic for certain VA. So I will have the torque speed characteristic for minus VA, correct? Yeah. If this one is the plus VA, I will have another one in the minus VA. And let's assume the load is bidirectional or unidirectional? Bidirectional. So simply, let's assume that the load is bidirectional. So this means that if this was TL here, then it will be somewhere here. Huh? Yes? So let's assume that this is T load clockwise. So this will be T load what? Counter clockwise. Someone will say up or down. Huh? Up or down. Good? Good. Now, in the first stage here, one, I was operating at this point number one, correct? Yeah?
Yes.
After that, what will happen? I'm doing plugging. Yes? I'm doing plugging, so automatically this curve or this line is forbidden. And I should go from 1 to 2, let's say. Let's point that point here to be point number 2. Should I fix this one or no? The two lines, should I fix them?
Yeah.
So you are getting the point, huh? This one is a solid line. One line. And this is the operating point. So I need to go from 1 to 2. How I can do that? The first thing, the machine will start to what? The current will start to decrease. Huh? This is the direction for decreasing the current. Until I'm crossing a 0 here. This 0, what? The machine is what here? VA is equal EA at this point, correct? And the current is equal to 0. Then I will what? Or the machine will build a negative current, correct? You know that I cannot go from positive to negative without crossing the 0. Yes, I must cross the 0. So crossing the 0, then the machine will build a negative or breaking current, let's say, in the opposite direction. So this actually can be seen as I break. It will be huge current, this one, huh? Actually a huge current. Then after that, the machine will start to deaccelerate until this point. Now here, if I'm disconnecting the load, yeah, and a mechanical drum is engaged, the machine will stop. Correct? Yes? Yeah? Why? Because here, without a mechanical drum, it will never stop. Why? Because the machine has energy. Still, there's inertia. Good? But in this point, 0 torque, 0 speed, without a mechanical brake, it will stop. Yeah? Here, if I need to stop it, I need what to engage? A mechanical drum or a mechanical brake. Yeah? If without a brake and the load is bidirectional, then the machine will accelerate in the opposite direction now. Yeah? Until reaching where? Minus. So this is actually also sometime in order to limit the braking or the reversing current here, we can add here what? Resistance in series. In order to limit what? The braking current. Yes? And this temporarily. Just only to limit the braking current. After that we can switch it out. Simply I can put parallel to that a switch. If I'm closing the switch, it will short circuit the resistance. Huh? And sometimes we can do something like this. Yeah. Of course, I should disconnect this line. Huh? And here, why I'm introducing a braking resistance in order to what? To limit the braking. Good? Yes, okay.
Braking current VA plus VEA على الresistance.
Yeah. Now if I need to IA will equal to what? Now if I'm specifying the sign like this one, then IA will equal to what? Minus VA minus EA over R total. Here I'm putting R total under the assumption that I can introduce what? A braking resistance. Yeah? If I'm assuming my direction of the braking current in the opposite direction, then simply I don't need the minus. You should understand that. The plus and the minus is sense of what? Of direction. Sense of direction. Good. Do you have any questions here?
دكتور point 2 بتكون السبيد نفسها بس
Yes.
reverse direction.
Yeah. Now, if the load is bidirectional, which means that the same load, the same voltage, VA minus VA, then this point and this point are identical in magnitude, opposite in direction. Yes? But if this one VA, this is minus 0.5 VA, of course it will not. Yeah? The lines, you know that when we discuss the voltage, armature voltage control, the characteristics are what? Parallel lines. Yeah? It's parallel lines. Yeah? Same slope. Because changing the, of course, this one without the braking resistance. Huh? If I change the braking resistance, the slope will change. So this will change the let's say in the end of the day, this will change the slope, but the final one, it will be the same. Yep. Good.
دكتور في عندي سؤال بأول سلايد إنه كيف كنا نعرف إنه فورورد أو ريفرس بس هذا إنه ممكن نحكي إذا مش ممكن هسه ممكن ناخذ محاضرة أو شيء.
No. Actually, straightforward. Plus or the minus will depend on the connection. So, for example, let's assume this plus minus VA plus minus EA. In order to decide in which Q I should know VA greater than EA or less than. Yes? Yes? Choose VA greater than EA or less than. Greater. So simply you will say that now. I'm having VA which is greater than EA and both are positive. Yes?
Yes.
So the current will flow from where to where?
From VA to E.
From the high potential to the lowest potential. So simply this will be the IA. And by definition, this is the plus. So the current here is positive. So because the current is positive, IA is positive VE, positive sign is the meaning. I can read this one as positive sign. Huh? Then the torque is what? Is positive sign. Why? Because by assumption, I'm fixing the field. Yeah. If the field is changed, I cannot say anything. I cannot discuss the operating mode. Why? Because maybe the reverse will be the forward will be reversed. You know that I can, let's say, reverse the direction of rotation either by changing the field direction or the armature direction. Correct? Good. Now, EA is positive or negative? From the plot. So EA is positive sign, so this means that omega is positive sign, yeah? So the power is the multiplication between the torque and torque omega, so is what? Is positive sign. So now, if I need to plot this one, where I will put it? In which Q? Yeah. So this is the Q1, which is the forward motoring. Why forward? Because I am in the Q1. Why motoring? Because the power is positive. Yes?
So اللي فوق الأول والثاني بكون دائما فوق. المربع الأول والثاني.
Yep. Why? Because by assumption, I'm assuming that the axe which pointing up is the positive axe.
Okay.
Yeah?
وصل.
Good. Anything else?
دكتور في البلاجينج مثلا بالسيريز وبالشنط ما بنقدر لانه بس نعكس الارمتشر فولتج مش حينعكس.
If I need to do this is a good question because in the book I think they discussed that. If I need to do a plugging for the series, I will disconnect the series field and I will connect it as a shunt, as separately excited, which means that I will reconfigure the machine. Yeah? The meaning. What about if someone needs to do, let's say, dynamic braking or plugging, let's say dynamic braking, dynamic braking for the series? What will happen? For the series connected machine, you know that here we have the series, and after that we have the armature. So plus minus, let's say V terminal here, RF here, LF here, let's assume RA here, LA here, and plus minus here. Now, if I need to do a dynamic braking by the name of dynamic braking, disconnecting the supply and here putting only what? A resistance. What will happen? What will happen? In the first stage,
field reverse to armature.
yeah. What else? While the current is reducing, the flux is reducing. So the speed will increase. Yeah? Because here the current is also, the armature current is the field current. So if I need to do that, what I will do? The connection will be like this. Here, I will reconfigure the machine such that the feed is supplied by the rated voltage, and now here I will introduce, let's say, the braking resistance. So this is very interesting. Why? I need to plot the torque speed characteristic. And let's assume that this was the torque speed characteristic for the series. And let's assume that I'm driving a load TL, and this TL is what? Proportional with the speed. Huh? Yeah. Proportional with the speed. Now I need to do a dynamic braking. How I can do that? We say the first thing, I will reconfigure the machine such that the feed is connected to the supply, while the armature is what? Is shorted by the braking resistance. So now the series is converted to be what? Separately excited. So the torque speed characteristic will change. Yeah? So it will be something like this. Huh? Yes? So now the machine will try to follow the torque speed characteristic, the new one. It will slide down, until reaching this point. Huh? Let's assume this is point 1, this is point 2, and let's assume this is the torque speed characteristic. Huh? What will happen here?
Stop.
This machine will stop. Yeah? Yes? Why? Because TL is equal to 0, and now the machine has no energy. Correct? No moment of inertia. It will stop. Yeah? Yes? Yeah.
يعني أنا سويتها هون زي كأنها شنط.
Yes, otherwise I cannot do the dynamic braking. Because if I will do the dynamic braking here, someone will say, okay, the current will start reducing. Yes? But the flux will start to reduce. Yes? So omega will increase. So this one will increase. Good?
طب الشنط نفس الشيء لازم نحولها separately excited.
Yeah.
لا. لازم نحول من شنط لسيبركلي.
The same thing. I should keep the flux constant. Yeah? What else? Good? Oh. If you don't have, let's see, any question, let's start with, actually this is chapter 3 in the book. I'd like to put it in chapter 2. So let's start with the actual chapter 3. Yeah? Which is the phase.
شو رايك ناخذ examples عليهم قبل ما ندخل بالشابتر؟
This one? Okay, let's see if you are lucky. I will put a slide for you. Okay, this one is empty actually. So let's.
عشان يعني ما نتلخبط.
Are you sure this is your tablet?
طبعا.
Huh?
طبعا.
Okay, let's see if this is your tablet. Yeah. So, شو اسمك؟
عمر.
Omar. So Omar is asking for example, and I think I have examples. I think I have one. Where is it? Somewhere here. Okay. So now let's discuss the following example. And for the example, we have a 440 volt, let's say DC motor, which has the following rating: IA rated is equal to 76 ampere at a speed of 1000 RPM. Of 1000 RPM. RA is given to be 0.377 ohm, and the rotational losses is 1 kilo. The rotational losses is 1 kilowatt, and the load for the machine is bidirectional. Now, the first thing, I need you to calculate the no load speed. Find the no load speed. Of course, this is separately excited. Huh? Separately excited DC machine. Okay? Calculate the no load speed. So, first one. Can you give me that?
EA بيساوي كي فاي دبليو
EA equal
كي فاي دبليو
K phi W and K phi
كي فاي على كي فاي صح؟ معي
So from here I can calculate K phi actually. I can calculate EA. Huh? K phi actually. Why? Because EA is equal VA minus IA RA, and K phi will equal this term over the speed. Yeah? Good? So I can calculate K phi.
KB.
Yes? Or KB, whatever. Huh? So I need to find what? The no load speed. And the no load speed will be what? VT over K phi. Yes? Do you remember omega equal to what? At this state, omega will equal VT over K phi minus RA IA over K phi, and this can be written as VT over K phi minus RA TE over K phi square. Correct? Yes? Yes? Good. Now I need to find K phi. So EA equal to what? VT minus RAIA. Let's see. VT is given.
Yes.
RA is given.
Yes.
IA is given.
Yes.
So this will be a piece of cake. Huh? So this will be 440 minus 0.376 multiplied by 0.377. If I do the math, this will equal 411.35 volt. And now I can find the K phi, which will equal E A over omega, correct? Now EA is already here, 411.35. Omega is equal to what?
1K.
So pi over 30 multiplied by 1000, 1000. And this one will equal to 11.96. So 111.96 rad per second. Yeah? The second thing, if IA is equal to 60 ampere. So if IA is equal to 60 ampere, during the regenerative braking,
دكتور احنا طلعنا فوق ال 111 شو هذا؟ كيف
No.
ولا اوميجا نو دوت هاي؟
لا هي كافاين نعوضها فوق.
I think it's already I calculated
No load speed.
the no load speed.
هي لا.
So from here I will find K. From here I will find K phi, and simply K phi it will be sorry. So omega. This at rating, huh? At the rate. Then omega naught will equal Vt over K phi, and this will be 111.96 rad per second. Thank you. Here I will find K phi. Now, if IA is equal to 60 ampere during the regenerative braking, calculate the motor speed. Okay, find the motor speed. Now, in which Q I am? Or let's say the torque is positive or negative. You know that if I need to find in which Q I need to know the torque and the speed.
نيجاتيف.
The torque is negative or positive?
Positive.
Why? The current is
IA
positive.
is positive.
And IA is 6 ampere.
اه.
So IA is 6 ampere, so the current is positive. Now I need to calculate what? The speed, correct? I need to calculate what? The speed at the regenerative braking. So simply this means what? Something like this, huh? If this is the torque and this is the speed, if I was here, I'm somewhere here now, huh? Yes? Somewhere here. And you know that the torque is proportional with what? With the current. So this one is 60. Okay. No, the 60 ampere. Sorry. The current is negative. I'm in regenerative braking. Yeah? Yeah. Here, I'm writing that I am in regenerative braking, but I'm giving you what the magnitude of the current.
اه.
I'm giving you the magnitude of the current. But the regenerative braking is deciding to be what? The current is negative. Huh? Good. So I need to find the speed at that point. Omega equal to what? Omega will equal Vt over K phi minus Ra Ia over K phi. Let's see, this will equal Vt 440 over K phi. This will be plus Ra is 0.377 multiplied by 60 over K phi, and if we find K phi from here, plug it here, and this will equal to, I think K phi will equal 3.93. So if I calculate this one, it will be 3.93, and this one volt second per rad. So if I do the math, this will equal to 117.5 72 rod per second. Oops. And this is correct because the load speed was 111.96. So this point here, the speed here is what? 117.72. Now what else I need? Okay, I need to calculate the braking torque during regenerating. Calculate the braking torque in the regenerating. Find the TB equal to what? What's TB? The torque is proportional with what? With the current. So this is actually indication for what? For the braking torque. And this equal to what? The torque.
omega في
The torque equal to what? The torque is proportional with the flux and the armature current. Yeah. So the torque will equal K phi IA. K phi is already,
No.
if 3.93 volts second per rad, this will equal to what? 3.93 Newton meter. Yeah? Per ampere. So this one multiplied by what? By 60. So it will be minus 3.93 multiplied by 60. If I do the math, this will equal minus 235.8 Newton meter. Now, what else? Is it enough or do you need more? Another example? Yeah? Let's discuss another example. Let's assume that I'm having a separately excited for 0 volt has IA rated equal to 76 ampere, the same thing, and also at 1000 RPM with the same RA, which was equal 0.377, except now the load torque is gravitational. The load torque is gravitational load. And for this drive, a dynamic braking resistance of, let's say, 2 ohm is used. Calculate the new steady state operating point. So simply, here is what. I'm having a machine separately excited, which is driving what? A gravitational load. Now, gravitational load, the meaning of the gravitational load is what? From this information, what I can get. Is the load unidirectional or bidirectional? It's unidirectional. Anything related to the gravity is unidirectional. All the time it's pointing toward what? The ground. Yeah? And we did a dynamic braking. By definition of dynamic braking, what I will do? I will disconnect the supply and I will install what? A braking resistance in order to limit the braking current. And the braking resistance, it happened to be what? Equal to what? 2 ohm. We need to find what? The new operating point, yeah? The new operating point. So, if this is my torque speed characteristic, and let's assume I was here, yeah, TL, and we did a torque speed characteristic, so I would go here, yeah, then the machine will deaccelerate crossing the zero and it will go here, huh? So I need this point, yes, the meaning, yeah, I need the speed at this point. Okay. So, how I can do that? Of course, here I can also ask you the magnitude of the braking current or the braking torque. So I need this point. Huh? Either I can ask you about TB equal to what, or IB is equal to what. Yeah? So, what I can do? How I can solve it?
احسب اوميجا لانه لو الدكتور ولا شيء.
Why I need that? Why I need that? Now, if I need to find this speed at this point, I need to find what? The back EMF at this point and divide it by K5. Yes?
From the
And I'm assuming that K5 is not changing, so this means that from this point I will calculate K5. Yes? Good? From this point I will calculate K5 because I'm assuming that I'm not changing what? The field. So from point 1, which is the initial point, huh? I can calculate K5. Who can give me K5 equal to what? It's 440 minus 0.377 multiplied by 76 over 1000 multiplied by pi over 30, and it happened to be 3.93 volt second the right. I think I gave you before, huh? It was. Yes. Did I make mistakes? Yeah, it's 3.93.
the point one and the rated here.
Which one?
Point one. The initial of
Yeah.
هي rated كان.
Yeah. Simply 440 has 76 ampere at 1000 RPM.
بس لا حتى لو ما كان عند الريتد بقدر اطلع كيف هاي صح؟ اللود يعني بس من النيم بليت يعني.
Yes, but simply you need the voltage. This line.
اوكي.
Without knowing the voltage of this line, how you can do that? So simply here I'm assuming that I'm having initial condition, which means that the machine has 440 volt, draws 76 ampere, and rotate at 1000 RPM. So, yes. Then
VA
VA, at which point now we are calculating?
Point
Point 2 or point 1? Let's go to point 2, huh? So, at point 2, VA equal to what? 0. Then we keep breaking. So, VA equals to 0. And you know that VA is equal to EA, yeah, plus IA RA. Yes? It's equal to 0.
مش لازم نحط هون البريكنج ريجستر.
Yeah. So EA will equal to what? Minus IA RA total. Thank you. I was missing it. So who can give me now EA equal to what? At this point, the current equal to what? Yeah, it's the same. It's the same line, huh?
same.
The same. So here, this will equal to minus, it was what? 76 multiplied by R total, huh? Which is 2.377. Yeah? So now if I need to find omega 2, this will equal to what? Minus this one, 0.76 multiplied by 2.377 over what? 3.93. And if I do the math, I think I did that. I did the math. This will equal minus 45.93 rad per second. Who can tell me TB equal to what? TB equal to what? Minus K5 multiplied by IA. So this will equal minus 3.93 multiplied by 76. And if I do the math, I think I did that. 173. It will be 173.14. In Newton. Question. I need to redesign the braking system such that the braking current is not allowed. By the way, the braking current is equal to what here?
The same current.
Okay.
In the opposite direction.
EA
The braking current at this point equal to what? The torque at this point equal to this point, huh? I'm asking about this one. The torque here equal to what?
0.
Negative.
T braking.
Huh?
Over K4.
اسمه
يصيرون
3 ما يسالون plus 1. So simply if I need to calculate the IB, it will be equal TB over K5. Even بسيط know that. I did not do that. But whatever, calculator. You have calculator? So it will equal this is minus, huh? So minus 173.14 over 3.93, and this will equal to what? Huh? Should I calculate it? Really? Congratulations. Mubarak.
دكتور مش هي نفس
مش نفس صح؟
ها؟
مش هي نفس السنة 6.
شيء.
احنا ضربنا 3.93.
سالب 44.05.
دكتور
No. This is not correct.
مش المفروض تطلع هيك ويطلع معنا نفسها هيك.
دكتور هذا التورك مش تورك بريكنج.
Yeah. No,
هذا التورك
this one is not correct. Sorry.
دكتور هذا تورك اللود صح؟
Yeah. So TB is equal minus EA over K5. Just a minute, huh? What is it? That's alright, this one. Sorry. But the answer is correct, by the way. It will equal EA over R total, correct? Yeah. So TB, let's write it here. TB will equal minus EA of 0.1 over R total. Yes? Now EA at 0.1 will equal to what? It will equal 440 minus 76 multiplied by 0.377, and this will equal to 411 to us, I think. Let's calculate it. It 411 points, it will be 411.35 volt. Now, if I need to calculate I braking, it will equal minus 411.35 over R total, which is 2.377, and this will equal to what?
سالب 173.
Thank you. Are you sure?
0.05.
So I was calculate here the current, right? 1.317
173.05
05
minus مش
minus ampere, right?
نفس الناتج الطلع.
Yeah. So the torque will equal to what? So this one is not correct. Right?
نفسه.
This I brake. So the torque now, T brake is equal to what? K phi multiplied by IB. So it will be huge, huh? Now, this one higher than the rated,
Yes.
2 times,
2 times.
3 times, no, 2,
Two
1
times.
time. Now, the question, I need to redesign the braking resistance such that the braking current is not allowed to exceed the rating.
Mm.
Understood?
Yes.
Who can give me how to calculate? So here we can, let's make space here. Maybe if okay, let's write another one. I have? Yes, I have. So now design RB such that IB is not allowed to exceed the rating value.
IP equal rating. So we
Yeah.
equal.
So IB will equal to minus 76 ampere. Yep.
Equal
minus 4.
الإي اللي حسبناها
Equal EA
اللي هي
from point 1
411.25
Over
over R total plus R
at 8. So this will be 411 point something,
0.25
point 05,
25
25 over 2 plus net it was 0.7.
2.376
minus 76. Equal minus 76.
Which will equal to, so this means that RB is equal to what?
Minus 411.25.
تطلع 503
Did you calculate it?
5.03
5.03. This is already,
RB كله
Yeah. according to this one.
يزيد
Yazid. So if you have any problem, call Yazid. He did the calculation. Yeah? Good. Thank you. Now I can rise the level such that I need you to calculate the braking resistance such that the machine will stop or will cruise the zero. Let's say will cruise the zero speed at 1.5 seconds. How I can do that? Huh? Key. Now, similarly, in the dynamic braking, and in this case, if I recall the torque speed characteristic, this is the first torque speed characteristic, the second one here. I'm assuming I'm having gravitational load. Now, this is the path that the current will follow. Yeah? And the machine or the machine will cross the zero speed at this point, yes? At this point, omega equal to what?
0
So, find RB such that omega equal to 0 at t equal 1.5 seconds. Like that.
بدنا نشوف
And to do so, I will give you
P
J equal to 0.1 and B equal to what? 0.01. So the time constant here will be what? 0.1. So,
G
and To make it easy, I will assume that LA go to 0. Which means that I don't need to care about the dynamic of the electrical part. Yeah? Only I need to deal with what? With first order ordinary differential equation for the mechanical part. Otherwise, I need to deal with what? Second order differential equation. One to describe the current, and the second one to describe what?
Speed. Speed.
Speed. The mechanical part. So how I can solve this? Or let's leave it as a homework or quiz.
بنناقشه بالمحاضرة
No,
الجاية.
no, no, no. This is a typical question in the exams. It's, by the way, this is a multiple choice equation. 2 points.
طب اللي قبله
Another multiple choice question. 2 points.
ليش اللي قبله اللي هو ازاي؟
The same thing. Okay. So simply, if I need to solve this one, I will go to say j d omega by dt plus b omega must equal te minus tl. Yep. Now, if I'm assuming there's a load, I will put it here. If I'm assuming there's no load and I'm disconnecting the load will be 0. To make it simple, let's assume that TL is equal to 0. In this case, I need you to find RB such that the machine will stop. Yeah? The machine will stop, which means the omega equals 0 and stay there forever. At certain time, let's assume 1.5. By the way, I don't know if there's solution for this one because I'm giving you roughly the parameters, huh? But I hope that it will be a possibility. Yeah? Okay. Now, let's see. So this will end up with j d omega by dt plus b omega is equal to te. Yeah? Yep. Now, te is equal to what?
No.
You know, this means that you need to find the transient response. Yeah? You need to find the transient response. So te will equal to what? T is variable. Yeah? It will equal to what? Minus k phi omega over r total. Yeah? Yeah? So T will equal minus k phi omega over what? R total. So if I put this one here, j d omega by dt will equal to minus b plus k phi over r total multiplied by what? By 1. This is what? A first order differential equation. Huh? Can I solve it? I can solve it. So this one has what? Initial speed, if I need to find the constant. The initial speed, I know it, 1000 RPM. The final speed equal to what? 0. Yes? So I will what? I will find what? The constant. So you can do that, huh? So the remaining is left for you to enjoy solving the problem. Okay, do you have any question?
بس تحكي ليش التي ناقص كيف هاي بيجي على التي؟ ليش على التي؟
This should be K5 here. This is the current. Huh? This is what? The current. So here the current IA is equal minus EA over R total. And we know that TE is equal to what? K phi multiplied by IA. Yeah? Thank you. Plus 1. No falafel for you. Next time. Huh? طيب. You have a question? يعطيك العافية.
يعطيك العافية دكتور.